Hey, welcome back to The Explainer. Today we're going to dig into one of the biggest ideas in all of computer science, the tree data structure. You might not see it, but it's the hidden foundation behind so much of the tech we use, literally every single day. So, let's kick things off with a question that every software engineer has to solve. How on earth do you organize just a massive amount of data? I'm talking billions of items, so that you can find one specific thing in the blink of an eye. Well, the answer, you probably guessed it, is all about the tree. All right, so here's our game plan for getting a handle on this. First, we'll nail down what a tree actually is. Then, we'll look at all its different parts, the anatomy, you could say. After that, we'll zoom in on a really powerful version called the binary search tree. We'll see how to actually use it, and then we'll take a little walk through the woods and see how to visit all the data inside. So, first things first. What is a tree when we're talking about code? Well, turns out it's a super intuitive idea. It's really all about organizing data that has some kind of natural ranking or hierarchy to it. When you strip it all down, a tree is just two things. It's got nodes, which are just spots that hold our data, and edges, which are the lines connecting those nodes. Seriously, just think of a family tree. Each person is a node, and the lines connecting parents and kids, those are the edges. It's all about showing relationships. Okay, to really talk about trees, we gotta learn the lingo. It's pretty simple, but knowing these key terms will make everything else just click into place. So every single tree starts at the very top with one single node, and we call that the root. Now, any node that has branches coming down from it is a parent, and the nodes they connect to below them, those are their children. And then finally, you get to the very bottom, the nodes that don't have any children of their own, and we call those leaves. See? Root, parent, child, leaf. It's all vocabulary you already know. Now let's get into a special, super useful type of tree, the binary search tree, or just BST for short. Now, binary just means each parent can have two children at most, a left one and a right one. But it's the search part, that's where the magic really happens. The incredible power of a binary search tree all comes down to one simple, beautiful rule. For any node in the entire tree, everything to its left is smaller, and everything to its right is bigger. That's 8. That one little rule is the secret sauce to its amazing speed. Okay, so we've got this one critical rule, right? Left is less, right is more. How do we actually use that? Well, finding something or adding something new is just about applying that rule again and again and again. Okay, let's do a little test. Imagine this tree has thousands of numbers, and we need to know if 57 is in there. You don't have to check every single one, you just follow the rule. We start at the root, 27. Is 57 bigger than 27? Yep, so we go right. Now we're at 51. Is 57 bigger than 51? You bet. We go right again. Now we're at 58. Is 57 bigger than 58? Nope, it's smaller, so we go left. And boom, there it is. But here's the most important part. Did you notice how at every single step, we basically threw away half of the remaining tree? That is what I call efficiency.
And if you look at the code behind this, it's doing the exact same thing we just did in our heads. It's really just a simple loop that keeps asking that one question. Is the number I'm looking for smaller or larger than where I am right now? And then it just hops left or right, getting closer and closer with every step.
And what's really cool is that adding a new number, like 45, works the exact same way. You start at the root and just follow the path where 45 should live. You keep going left or right until you hit a dead end, an empty spot. And that's exactly where the new node gets plugged in. And yep, the code looks almost identical. It just walks down the tree to find that perfect empty spot, and then it links the new node as either the left or the right child of its new parent. It just goes to show you, both finding and inserting data are driven by that one powerful rule. That's what makes them so fast. So we're good at finding and adding one thing at a time, but what if you need to visit every single node in the tree, maybe to print them all out or something? Well, this process is called traversal, and there are a few different ways to do it. And the order you choose matters a lot. First up, and probably the most important one to know, is called in-order traversal. The pattern is always the same. It's like a little mantra. Go all the way left, visit the node you're on, and then go right. Left, root, right. That's the rhythm. And check this out. This is the really cool part. When you do an in-order traversal on a binary search tree, the values come out in perfect, sorted, ascending order. Every single time. That's not an accident. It's a direct result of that left is less, right is more rule. It's an incredibly powerful side effect. Next, we have pre-order traversal. Here, we just change the rhythm a little bit. You visit the root first, and then you go left, and then you go right. So root, left, right. This is super useful if you ever need to make an exact copy of a tree, because you save the parent before you deal with its kids. And last but not least, there's post-order traversal. You can probably guess the pattern by now. You explore all the way left, then all the way right, and you visit the root node dead last. Left, right, root. This one's often used when you're deleting a tree, because it makes sure you get rid of the children before you get rid of the parent. So let's just recap that real quick. We've got 3 main ways to walk through the same tree. In order gets you your data sorted. Pre-order is your go-to for copying, and post-order is perfect for deleting. Same structure, 3 totally different and useful ways to read it. So, what's the big picture here? What do you really need to remember? Well, trees are how we structure data with relationships. The binary search tree, with that super simple left less, right more rule, gives us lightning-fast searching and inserting. And these different traversal methods give us flexible ways to get all that data back out.
But there is a catch. All that speed relies on the tree being nice and bushy. What happens if you add numbers that are already in order, like 1, 2, 3, 4, 5? You don't get a bushy tree, you get a tall, skinny, pathetic-looking chain. And searching that is just as slow as searching a list. So that brings us to our final question. How can we make sure our tree always stays short and balanced, no matter what we throw at it? The answer to that? Well, that's the doorway to even more powerful types of trees. But that's a story for another time. Thanks for joining us on The Explainer.